Okay, so let me share.
Professor, if you're, oh, okay, now I see it.
Yeah, thanks, Gilberto. Yeah, so this is the platform. We have the third test on April 26th, and then the final exam the week after. So everything we do from here until the end is like exam review, okay? And like before, the questions that are on the platform are similar to the ones that I asked on the exam. I'm sure you want to know about your exam grades. I do not have them yet, but hopefully for next week, I should for next week post them. And then we can talk about those exams. Um, any general feedback you want to give me about the part 2? How was part 2?
I think it was a little confusing.
You guys didn't let me know it was confusing. You have to keep in contact with me.
Yeah.
You got stuck?
Yeah. I got stuck.
Anybody else? Okay, well,
Yeah, I
Honestly, I had to see the
agree.
videos
Oh,
like 2 times to make sure I was able to do it.
that's okay. You can do it 2 times, 3 times. That's the idea. Don't feel bad about that. Whatever it takes. So, yeah, I'll have to look at that. I haven't even looked yet at the part 2 to see. You guys should have put your answers on the actual exam document to make it easier for me to grade. And I'll see how that went. And then I'll look into your formulas to see if anything went wrong. And as usual, I'm very generous, so I will look at how you did. Okay. And then we'll talk about it more. So we need to review a little bit of everything for the final exam. So you're going to see every topic again. So it's not going to, hopefully, there's not going to be any confusion by the time we write the final. All right, so we're going to start Unit 5. Now for Unit 5, you need to review statistics, okay? The statistic review documents are here. Here's the paper document. So there's all of these documents here for review. And then there's the videos down here. Okay, so there's 1, 2, 3, 4, 5 hours of statistics review. What you need to get out of that is a very particular part of statistics. Okay, there's lots of areas, or there's a lot of topics in statistics, but we're going to be focusing on regression. That's where we really end up. And the best example is the final exercise that I do where I discuss financial data. So I do a review of statistics, just talking about statistics in general, and then I narrow in on financial statistics. Okay. Then, presuming you did that or you're competent in statistics, you should be able to understand Unit 5. How many of you did not take statistics? Did not finish taking statistics? It's simple linear regression. You can put it in the chat. Let me know. You didn't finish? Sorry for the
Well,
shock.
no, it's okay. I'm taking it right now. That's fine.
Okay. So you're going to need to do the review, right? Anyone who hasn't finished statistics needs to do the review, which is not actually a review, but it's like an introduction to the main topics. Okay. So this is a problem with our program. A serious problem with our program is that statistics should be finished by 3106. And it's not stressed nearly enough. That's why I have the review in here. And I think it's good because it leaves out the stuff you don't need and just focuses on what you do need. What I can do, there's 4 of you, and right now, let me see, there's 13 in here, 12. Okay, so it's a small fraction. Is everyone else competent in statistics? So if I show you, if I open this document.
With the naked finger, go buy him a ring. But the crazy part is someone.
Yeah, you guys are going to need to turn your cameras on so you guys can focus on what I'm talking about.
Professor, I'm not gonna lie. The camera on my computer is not working,
Uh-huh.
but I can try.
Yeah, you can try. It'll help you be more attentive. Okay, so in the review, I'll go with where I end up.
Professor, my camera is supposed to be on. Is it working or no?
It's black. It's black. Mauricio is following instructions. You guys get on the cameras. So this is where we end up. Let's start here. So I'm going to do the wrap up of the review of statistics for people who haven't done statistics yet. And I need you guys on the cameras.
Professor, my camera is on. Is it working?
Yeah? Maybe are you covering the camera lens?
No. I mean, it's not supposed to be covered. Let me a freaking second. Oh, you gotta be kidding me.
You are covering it?
No, apparently this computer has like something that covers the camera.
Oh.
This is something that should be in the instructions. What the heck? Okay, this makes a lot of sense now. Okay,
Uh-huh.
what the hell? Okay, so
Welcome.
if I do this, wait, no. What the
Franco, you're being
fuck?
recorded. Should I pause? Should I pause?
What?
I'm gonna pause.
Nah, I'm here.
Okay, okay. All right. Nobody else wants to get on? You guys get on. I'll give you a minute. Okay. So can you guys see this is the document that's called Risk and Return Revised. It's new from last semester. Okay. All right. So here are some data. So for people who took statistics, or even if you didn't, these are 2 variables. And from I'm asking here that you calculate. I'm trying to clear the screen. Can you guys see clearly? Because I can't see the view you see, but a financial analyst provides you with the following, what I call ex post data, and that's different from ex ante data, and I will explain that when we get there. But right now you just see pairs of data for variable X and variable Y. X, if I was to graph this, X goes on the horizontal axis and Y on the vertical axis. Can you plot the data while we wait for Paris and whoever else? Can you plot the data in a graph on like a chart, a coordinate axis? Okay, so you're going to plot the data. I'm going to put my iPad up. You see my iPad? It's just a blank screen.
Yes.
Okay. And all right, I want to make a straight line. Sorry. The only way I know how to make a straight line. And just in terms of statistics, this is X, this is Y. And I start to plot, I'm going to put that lowest number is 8 and the highest number is 15. So I think I can go by 5, right? I probably could go by 1. So 5, 10, 15, 20. And then we got a little bit more here. I was looking for graph paper. I'm sure I have graph paper, but I don't know how to get it up onto here. Okay, so the first point is a pair of data, 15 and 30. Oh, sorry, the second Y goes from 15 to 30, so I'll see this as, I can see this as 15, 20, 25, 30, and I'm going to put a break in the graph. So this just means I don't have to start at 0, 0, okay? This makes it easier. Okay, so I'm going to plot 15 and 30. X is 15 and Y is 30. And I'm going to put a dot there. Something like that, right? The next one, 9 and 18. 9 is about here and 18 is about here, right? And then 10 and 20. 10 is here, 20 is about here. And then 7.5 and 15, 7.5. Oh, what's wrong with my graph? Something's wrong. Hold on. What did I do? 10 and 20. 10 and 20. Oh, it's not going to work. I really have to do the right thing. Hold on, hold on. Okay, wait a second. Let me put the scale properly, or I'm going to lose my point, I think. So if I'm going to do 5, 10, 15, 20, then I have to make this just longer here. Get my ruler back. Sorry about that. Are you guys drawing? Don't just look at me. If you do it, it's more likely you're paying attention. So, all right, so 15 and 30, 15 and 30, 5, 10, 15, 20, 25, 30. And so 15 and 30 puts me up there. And then 9 and 18, 9 and 18 puts me about here. Here. And then 10 and 20 puts me here. And 7.5 and 15 put me 7.5 and 15 might put me here. This is the problem is my scale. And then 8 and 16. 8 and 16 put me like here, my per scale. Okay, I'm not going to put that one on. Okay, so they should be, what you see is what? What do you say when you see this graph? How do you
It's linear.
summarize this graph?
It's linear.
Everyone agree? That's how you comment, right? It's a lot. It looks like a line. In fact, it looks like these points fall exactly on a line. That's how you comment. All right, so this is a line, it looks like, and they fall on a line. Is it necessarily the case that two pairs, a pair of data fall on a line? Is this always going to happen that a pairs of data fall on a line? No, right?
No.
No. So it could be like, so that's the sort of thing we're used to. This is known as a scatter plot. And with a scatter plot, it's not a line exactly, but we could argue that we can use in statistics, we estimate a relationship that looks like it's linear between two variables to be able to make predictions. So if we think that there's a slight, so you can call it a slight or strong, like how would I refer to this one here, this example here? What kind of linear relationship is that? Is that moderate? Is that strong? Is that so everything is relative in statistics, okay? So when I look at this one that I just drew and the one that I painfully drew before, which one is more linear or stronger in the relationship?
The second one.
No, the first one. So this is a strong,
That first one.
linear, and also you want to say positive relationship. Okay,
I
because
think this one. Yeah.
say it.
No, I was gonna say that the second one would be considered weaker. So like since it doesn't follow like a linear structure, I would say.
Yeah, it's not all on the line, but it's still a moderate, linear, positive relationship, wouldn't you say? Why
Wait,
is
is
it
there two
positive?
lines? I don't know. I
You
can't
can't
see the
see?
other line.
You don't see my other line?
I see one line,
Just
like in
one
the
line.
second one.
Yeah, there's a
Oh,
line here.
okay.
So the dots themselves, the pairs do not make a line like they do over here. This is an extreme case, okay, where they're perfectly on a line. This is a scatter. These are scatter plots of the pairs of data. 1 minute, okay? I'm just gonna. Okay. So this is a scatter plot where this one is different than the original one because this is a moderate linear positive relationship. This is a strong linear positive relationship. What am I referring to when I say strong? It's how well the pairs align. Okay. In other words, how well X can be used to predict where Y will be. Now let's go back to the data for a moment and we can see it in the numbers. It's very clear in the data itself. What do we see when I make you look at the data itself? What do you see? What's the relationship between the variables?
They double.
They double, right? That's it. They double, and they double perfectly. That's the point. The fact that they double perfectly, the perfectly part, is what makes them fall on the line. The doubling part tells us what? All right, so what we're going to do now, hey, well, let's see if anybody knows the answer. I want to see if anybody knows the answer. So the perfectly part, the fact that it's perfect, 15 makes 30, 9 times 2 makes 18, 10 times 2 makes 20. That perfect part makes it on a line. I can get one from the other. If I told you something that was not here, what if X was 5? What would Y be?
10.
Yes, if we assume the relationship holds always, then we can estimate that when X is 5, Y is 10. What if X is 1? What's Y?
2.
2, right? It's just exactly that.
If X moves 1, then Y moves 2.
Exactly.
but
Exactly. All right. So I want you to take your calculators. You all have your calculators, right? I want you to take your calculator and I want you to put this data into the statistical mode of the calculator. Does anyone know how to do that? Or can you guess? You guys guess while I set up the exercise on my iPad. Just try and guess, use the stat mode. Look where it says stat, look where it says data. You're going to enter into data and I will show you. You're going to enter the numbers into data and then you're going to get the results in stat. Did anybody get it?
Put in the values on X1, Y1.
Very good. Okay, so I'm going to do it for people. Oh, sorry. I'm going to use my calculator now to do it. All right, so I'm going to put in the data, second data, and there's something already there. What should I do? I should clear this, right? So I say second, clear work. So now it's clear. And I begin to put the pairs of data. X gets 15, Y gets 30. Use decimals. Use decimals. For what I want to do, it's going to be better to do decimals. So get the habit, 0.15. And I hit enter and scroll down. Now put the Y in. 0.3, enter, down. That's the first pair. Keep going. 0.09, enter, down. 0.18, enter, down. That's the second pair. 0.1, enter, down. 0.2, enter, down. 0.075, enter, down. 0.15, enter, down. 0.08, enter, down. And 0.16, enter, down. I did 5 pairs. I entered 5 pairs of data. Everything I'm reviewing, and looks good. All right. When you're done, let me know. Are you done? Are you put it in the chat that you're done? Okay, you're done. Now what do you do? What is your instinct? Or what do you know you have to do?
Compute something.
Yeah, well, do you see the word stat? You need to activate that. Second stat. That will give you your results. It says LIN. What does LIN stand for?
Line.
Linear.
Line,
Linear.
linear. Perfect, perfect. So these are the linear results. And so N is 5. That's the sample size. So you did it right. There are 5 observations. What's this?
Median, right? Or something? Or the mean?
That's the average. That's the mean of the X variable. The mean of the X variable, 9.9%. Okay, so you can write that down. And then we keep scrolling. So it just gives you the data for the X, the data for the Y on their own, and then it gives you the results of the what's called a simple linear regression, trying to fit the values on a line. So I keep going. That's S for X. What is that?
That's the median, right? Or
No, no.
I mean the la otra, la mediana. And I forgot the
No, no, but thank you for being
That the
bold and putting it
deviation
out there.
standard, I think. Is that the deviation standard? But
Excellent. Yes, yes, that's correct. It's Christopher. So that's the standard deviation standard. That is the standard deviation of the sample. That is the standard deviation of the sample because it's different from this one. What's this one?
La varianza, I think. I forgot how to say it in English. I think it's la varianza.
It's not the varianza, but most students would probably say that. This is the standard deviation as well, but when you see a Greek letter, that's a Greek letter. That's sigma. It's a S in Greek for standard deviation. But is the standard deviation thinking or imagining that the population, the data is a population of data, not the sample? When you assume the data represents the population, the calculation is a little bit different. What's the difference between this number and this number? What's the difference? Which one's bigger?
standard deviation.
Of the sample. The
The
sample standard deviation is a little bit bigger than the one from the population because we divide when we calculate. Okay, so let's talk about these what we're doing here. Okay, let's go back to, before I continue, I'm going to go back to the document. Let's look at the document. So what the document says. Oh, I have to share the document again. So you guys didn't need to know anything about statistics. I'm starting from 0 here in statistics. So some of you have this knowledge, but don't assume you understand either. Please stick with us. Okay, this is the formula to calculate the average. We saw X bar, right? This says sum the values. That's a Greek letter too. That's another sigma. It's a capital sigma. It says sum all the values and divide by how many. So this is the average. Whenever you see this symbol, this is a sigma summation symbol, and an n fraction here, 1 over n, that's an average. Using the same logic and looking over here, what is this in here? We have the same thing with the sum, and we have n, but we have like n minus 1. It's a little bit smaller. This here is called the variance. This is the sample variance. That's what that is.
Professor, your screen is still on the calculator.
Really?
Yeah.
I thought I clicked the wrong one. Here. Thank you. All right, so back to this. The sample mean formula says add all the x's together and divide by how many there are. This is an average. This is the symbol for the average. This symbol here is a summation symbol. It's also an S in Greek letters, but I believe it's the capital S for sum. So most of you know, so this is the general symbol for sample, the sample mean, right? Sample mean. Most of the time, 99% of the time, we're going to work with the sample mean, but I'm going to also talk, well, and you're used to working with the sample mean. In this class, I'm going to work with the sample, and I'm also going to work with the understanding of the population. All right, so stick with me. So this is the sample mean. Whenever I see the symbol, summation, and I divide by how many there are, this is index from 1 to n, and then I divide by n, the sum by n, I have like an average or a mean. The same thing here. What is this called? Some of you said it before.
Varianza.
That is the variance. The variance, excellent, is the average of the square deviations from the mean. So this in here is a deviation from mean because it's taking every value and subtracting the mean. It's trying to find out how far all the values are away, but getting an average notion of how far away, how spread out the data is. And then it takes an average, but it doesn't divide by n. It divides by 1 less. What is the effect? That's the most important thing. What is the effect? When you divide by 1 less, the number is a little larger. That's why you see S is bigger than the sigma in the results. Why do they do that? Because statisticians discovered that this estimator was biased. It was a little bit off. So to protect against that, they allow, we only divide by 1 less, so that the number overall becomes bigger, right? If you divide by a smaller number, the overall number is bigger. So this under here is called the variance. And when we take the square root, we get what?
Standard deviation.
Standard deviation. Why do we take the square root?
This has something to do with the negative, right? Or like a fraction, the 1/2.
Something to do with the negative. Yeah, if we're going to go that far. Yeah, but let me see. I'm going to broadcast this. No, I don't want to do this one. Just a second. This is really important. I don't know how to stress enough how important, but it's important. Okay, I'm going to go back to my my iPad. Okay, so what I was saying, when we do this, okay, let's say we did this. Let's say we took x minus x bar. What was x bar again? What did we find out? Right, we had 9.9%. What are the units here? What variable, sorry, what are the units of these values? %15.
1%.
So let's say I took x minus x bar, just made a column here, deviation, the deviation from the mean. So what is 9.9? Sorry, 15 minus 9.9. I don't want to write there. It's gonna be messy.
5.1.
It's 5.1. Everybody agree? Now look at the formula. So I calculated this, and then what do I have to do? What's the next step? I square it, right? What's 5.1% square? I'm gonna call somebody else. Mauricio's not gonna care, you guys. Joshua, what's 5.1 square? Ehrlich, what's 5.1 square?
26.1.
36?
26.
26? Yeah, that makes more sense. 26.1. And what do I say? Is it percent?
Yeah, X%.
Are you sure?
Wait a sec.
When you square the value, you also square the units. This is actually percent square. What does percent square mean? It basically means percent squared. It doesn't mean anything in terms of what we're operating in. And that's why when we finish calculating the deviation of the mean all the way down and squaring them all the way down, and then we take the average less 1 because I told you so, or this is how we do it in statistics for samples. When I do all of that, at the end, what do I have to do? To remove the square.
A square root.
That's what it's for.
Square root it.
So we have to square root it. We have to square root it. Now, why do we square in the first place? That's a different question. Why am I doing this? I'll tell you that in a minute. So everyone agrees that if I have all these numbers here squared, and then I sum them, they're going to be in units percent squared. That doesn't make any sense for us. We need to return it to the original units of percent. To do that, we use the square root. Now, going back a step, why did we even square it in the first place? Why do we square these numbers? We want an average. We want a measure of the spread, how spread out these values are, to be able to talk about you know, we want to make predictions and statistics. And if you watch my reviews, I'll explain all of that. We want to make predictions. Well, we saw in this case, our predictions would be really good because in general, for the 5 values within this range of data between X being 8 or 7.5 and 15, the relationship was perfect. All we had to do was double. To get there mathematically, I'm going to show you, we're going to go through all these different calculations. But to get there, I need to calculate a measure of how spread out the data are. And when doing that, I want to find out, okay, how different is this from what we expect? So the mean is like an expected value. So if you had to bet on it, what would be the S&P 500 next year if this was what it was every other year and things are pretty stable? Let's say the economy was not changing much. So variables or factors that may change the return on the S&P 500 have stayed relatively stable. So we can expect in the next year that the return on the S&P 500 would be, for every dollar invested, the returns are 9.9%. So for every $100, you get about $10. That's what that says. On average. Okay, so that's what you would expect. That's what you would bet on. How
Is BCE a different ETF or?
it's going to be a stock. It's going to
Oh,
be.
okay.
Right now, I'm going to talk about loosely just about 2 variables, and then I'll put it all together why we do this in this kind of order. But right now, I just want to focus on the statistics part. So I want to calculate how variable, you know, what's the variation from the expected value, and I want like an average measure of that. But if I do that, if I get the deviations, let's do that. Let's do the deviations from the mean all the way down. Let's keep going. What's 9.9? Sorry, 9. What's the deviation? 9 minus 9.9. What do you get?
Negative 0.9.
Okay. And what's about 10 minus 9.9?
10 minus 9.9, it would be equal to 0.1.
Right? And what about 7.5 minus 9.9?
That would be 2.4.
And what about 8 minus 9.9?
1.9.
Negative, right?
Yes.
All right. So let's say I just wanted to get the deviation from mean and the average of the deviation from the mean. What happens if you try and get the average here? Do you know how to get the average on your calculator?
No, I do not know.
Well, you add them up and divide by 5.
And divide by
Add them up
numbers.
and divide by 5. What do you get if you add them up and divide by 5?
Uh, 2.08.
No. Try again. Be careful with
I
your.
got 0.
Who got 0? Anthony?
Sebastian.
Got 0 too.
How many of
Yeah,
you
same
got?
here.
Everyone got 0 when you add them up? Just be careful here. This is a 2.4, not 2.9. So when you add these up, you got 0. Is that a mistake or is that just a coincidence for these numbers? Or will that always happen?
$50-50. Someone say it always happens.
Okay, it will always, always happen. And that's because the mean, the average, is the center of gravity. It is the point, it is the value that is closest to all the points. So if you try and calculate the deviation from it, you're going to have some values. So if I think about a distribution, which again, if you guys have no idea what I'm talking about, make sure you watch my review, okay? I do all this in the review. So this is like a distribution of the data and the mean is in the middle. and the data is all around it. X bar, no matter what a distribution is, even if a distribution looks like this, X bar is the value that balances the distribution. It makes sure that the weight on the left is balanced by the weight on the right. Okay, so if I'm trying to calculate the deviations from the mean on this side and the deviations of the mean on that side, they're going to perfectly balance. So of course, some of these will be negative, the deviations, so the values on this side will have negative deviation from the mean. And the ones over here will be positive because they're higher than X bar. And what happens when you add them together? You get 0.
When
Okay.
I add them together, I got negative 0.5, but I don't know if that's correct.
No, it's incorrect, Gilberto. You did something wrong with the you got to be careful when you enter the negative values. Let me do it just to confirm. And this will always happen, okay? This will always be the case. I'm going to share this, split the screen with so I'm going to put in here, hopefully these are the right numbers. So I can just add them, or I can use my data mode, my stat mode again. I can clear this, second, clear work, and I can put it in here. 5.1, enter, down, and I just skip over the y's. I just do it for one variable. 0.9 negative, enter, down, down. I skip over the y's. 0.1, enter, skip over the y's. 2.4 negative, enter, down, and 1.9 negative, enter, down. Did I do it right? Let's check. 5.1, negative 0.9, 0.1, negative 2.4, and negative 1.9. Okay, and here is the moment of truth, second stat. And yeah, okay, I can get the linear regression from here, but I can also get the mean, and the mean is 0 because the sum is 0. Because the sum is 0, when you take 0 and divide it by anything, you're going to get 0 back. All right, so it will always be the case that the deviation from the mean, because of the mean being the balancing point, and it balances the weights on the left and the right of the distribution. In this case, it would be a little bit more over here to balance this weight with this tail. It will always be 0. So how do we deal with the fact that all we want is what we want is a measure of spread of the values, but we don't want this to happen because obviously, you know, it's 0. What we really want is to forget about the negatives. And this is Mauricio, you were saying something about the negatives is the issue. And it's true. I need to get rid of these negatives and then just care about how far all the values are from the mean. And you can do that by completely just forgetting about the negatives, but statistics has been developed doing something else, squaring the values instead. And that gets rid of the negative, because when you square a negative, you get a positive. So then you sum up these and take the average of these. Those are the steps. And you average by dividing by 1 less, for the reason I told you that statisticians noted that it was a little bit off as an estimate when you did this. In higher courses in statistics, you actually prove that this is the way that this is the better or the unbiased estimate of the standard deviation. But because of this square here, you have to take the square root. So I'm never going to test you on the origin of the formula. I just want you to appreciate what you're doing. You're calculating an average. Statistics is about averages and relative measures. That's what it is. That's what we're doing. You're always going to see the sigma thing going on. And you're going to see it as we review the other calculations that we make here. Okay. So far, what we've done is calculated the mean for X. We've calculated, what's this called again? Let's see, let's do a little review. This is called well, it says here, variance of X. But be careful, these are the sample results, right? These are all the sample statistics. Okay, there's a sample statistics. Well, actually, statistics come from a sample, and I explained that too in the videos. But okay, so these are at the end when you sum this and average, you have to take the square root to return to the units of the problem. So then these are back to standard. These are back to being percentages. All right, let's continue. Let's go back to our calculator and see what else the calculator gives us. I have to re-enter my values, unfortunately, because I
Professor, I did everything like you did, and my calculator just ends up with negative 0.1. I don't know why.
yeah, you did something wrong. Did something wrong because
Yeah,
it
that's
has to
what
be
I'm trying to
zero.
find out.
But that's the point. Okay, the main point is that you will always get zero. If you didn't get zero, you did something wrong. Okay, so I'm going to re-enter this data. Actually, I need the split view. All right, so I'm going to re-enter because I lost it. So I'm going to put in here second data. So for people who didn't do it, let's do it again. So 0.15, enter down. 0.09, enter down. No, I did it wrong. So 0.3, enter down. 0.09, enter down. 0.18. So I'm just repeating what I did before. You guys can catch up if you didn't do it yet. 0.2, enter down. 0.075, enter down. 0.15, enter down. And 0.08. I'll review my values to make sure I did this right. All right, so 15, 30, 9, 18, 10, 20, 7.5, 15, 8, 16. Okay. And I was going through the results, second stat, and I was seeing that these are the linear results. It gives me 5 observations, and the small n represents the sample size. This is the mean of X, the average of X. This is the standard deviation of the sample for X. This one is the standard deviation dividing by 5, not by 4. Okay. And it's assuming if you want this one, it means that you believe you have the population of data. In other words, it's not just a sample, it's all the data available. And the calculator is giving you both, so you get to choose which one you want. And for our purposes, we just want S. Now it gives us the results for Y. This is the mean of Y. This is the sample standard deviation of Y. And this is not the variance. It is the population standard deviation of Y. And now, drum roll, we get A, B, and R. What are those? What's A, B, and R? We got a bunch of other things, but we're not going to go there right now. Does it look familiar? A, B? Well, B is 2. What is 2 for us in this problem?
Like the ETF and the company, like the two.
No, no, but you're
Uh,
getting somewhere.
Is that the slope?
Is that what?
La pendiente.
So that is the slope, the 2, the doubling. The slope is the doubling, okay? They go from 15 to 30, 9 to 18. That's a doubling. So that is the slope of a line of the linear relationship between X and Y. In this case, the relationship is perfect. They perfectly fit on the line. That's not normal. It's just for this example I've given you to make the point that if it's perfect, your correlation coefficient will be 1. That's what that is. So let's talk about that if you've never seen this before. So what we have here we've done so far the sample mean, the sample standard deviation, which is all this, which we easily get out of our calculator. Do you agree? I don't expect you to do one by one, making tables. You can get it out of your calculator from now on, all right? But I'm trying to show you that the origin of this. Hopefully that helps you understand the theory better. We are interested in how these variables co-vary. How do they co-vary? When x goes up, what does y do? When x goes up, does y go up or down?
Up to
Up.
20.
Relatively, right? So up from, so when it goes from 9 till 10, what happens to y? 18 to 20. Okay, so when x goes up, y goes up. And it's consistently like that. So this measure here, covariance, captures that. It shows you the direction of the relationship. What did we say the direction was when we drew the graph?
Positive.
We said it was positive. When x goes up, y goes up. Also, when x goes down, what happens with y? So when we go from 10 to 9, what happens with y?
Goes down to.
Okay, so when x goes down. So a positive relationship is a reinforcing relationship. So when x goes up, I mean, they're going, one's going down, the other one's going down. It's that the notion of positive or direction is that they do the same thing. What if x goes up, but y goes down? What do we call that?
It's a negative relation.
Negative. What if x goes down and y goes up? So the fact that they're reverse is also negative, okay, when they reverse. Okay, we call it this one positive, this one negative. The idea of positive or negative shows up here in what's called the covariance. Covariance. Oh, I want to use an arrow. Okay. This gives you the direction of the relationship. Notice, look at the formula for a moment, and what does it look like? Does it look like anything else on this page? What do you see in this formula that we saw before? Let me make it, I think it's cutting off the screen. Let me clean this up a little bit.
But the mean by
Yeah,
the
yeah. So you see the averaging again, okay? So statistics is about averages. Averages and relative measures. If I write this one over here like this, can I write that instead of this? Can I write this like, oops. Can I write this one like this? Does everybody agree with what I did? Because it says square, so I can put two beside each other, right?
I don't think so.
You don't think so?
I don't know. It looks wrong.
It looks wrong. It's not wrong, because this just means two of them. When I square, I just times x by x, or in this case, deviation from the mean times the deviation from the mean. So it's not wrong. Did I convince you? So I can do that. Doesn't it look the same here? Except that I do it with y. So this is a variance, but it's a covariance. One factor is X, the other factor is Y. So let's say, let's go back to talking about this again. And let's say if X, okay, if X goes up, what sign will this be? If X goes up from X bar, what sign will this be? We're going to replicate this here. So when X goes up, this will be positive. And if Y also goes up above its mean, Y will be positive. When you multiply them, what do you get? When you multiply a positive and a positive, what sign do you get?
Positive.
Now let's say X goes down below its mean. This will be a negative. And then let's say this one was a negative 2. What is negative times negative?
Positive.
Positive. That's how this formula works. Okay, so that's showing the direction. If and using the mean as the relative measure, when X is above its mean, that's a positive, and then Y will be above its mean too. That's a positive. That's a positive relationship. If you see that pattern, what if you see, I'm running out of space. Let me do that again. What if X goes below its mean? So this is smaller than this one. You're going to get a negative, right? But let's say at the same time, Y goes above its mean. What do you get? If you multiply a negative and a positive, a negative. And what if they're opposite? What do you get?
Negative.
A negative. So it's the average tendency of the relationship that's getting captured here. So this is just going to give you the direction. Covariant. I explain, like I said, more details in the videos if you want to go and see what I do there. But I just want to get through these formulas right now. So that's called the covariance. Now, if I take that number for these two variables, the sign is going to tell me if it's a positive or a negative relationship. When X goes up, Y goes up. That's a positive relationship. When X goes down, Y goes up. Or when X goes up, Y goes down. That's a negative relationship. That's going to be captured here. The problem with this measure, because we like it because it gives us the direction, but it doesn't tell us anything about how tight that relationship is. It doesn't tell us how well it fits on a line, which is really important. If you see a trend, let me see if I drew something right over here. No. Nope. I drew a lot of things. Okay, here. So this, so we understand the direction. This is positive. This is positive. Let's draw a couple of negatives. What if the data look like this? What do we call that? Or how do we describe that?
Strong linear negative.
Right, perfect or strong, negative, linear relationship. Usually you're not going to get exactly a perfect relationship. You're going to get something that looks like something like okay, so that one is even worse in the line than the one I did over here with the positive, right? Maybe make it smaller. So this one we're going to call, again, It's like a weak. This is weaker. So we're using words, but we want to get a number, a metric, a measure of that. This is a weak, negative, linear relationship. So to capture all these words, we have a statistic that's called what? Okay, let me go back a step. What will be the covariance for this relationship? Positive or negative?
Positive.
Right. What will be the covariance for this relationship?
Positive.
Also positive.
And these ones will be?
Negative.
Negative. So it's telling me the direction, but I want to, there's a difference between these. I need a measure of what that difference is. So what I want to do is from data sets, from pairs of data to pairs of data, convert this in a standardized way. Basically what I do is I divide by the standard deviation of the X and I divide by the standard deviation of Y to get a measure called the coefficient or the correlation coefficient, or just correlation sometimes it's called. It's a symbol R, and R is really just the covariance divided by so standardize. We standardize. We divide them by how spread out X is, how spread out Y is, and we reduce R to an index. It's not a percentage anymore. R is an index, and it goes between -1 and 1. And as for any pair of data, we reduce the relationship to a range of values. Now, you have to be careful. You can only, in finance, obviously, you're using quantitative data. R can only be calculated with 2 quantitative variables. Okay, you can't do it. You can't make an R like this with something like a variable of gender or something like that. That's not quantitative, or a variable of, anyway, that's just my immediate example. But you need to have quantitative data. In finance, you do. So obviously statistics is used a lot in finance because the data is quantitative and continuous. Okay, what does it mean? So let's see these, let's go through these pictures just to understand how R works. So what would the R be of this? So covariance is greater than 0, but what is R here? Approximately. If you had to guess, and you don't completely understand what I'm doing yet, it'll be positive because R also gives you the direction. It doesn't change the sign when you divide by 2 values that, well, these are standard deviations. Standard deviation will always be positive, right? Because the standard deviation is the square root of something, which will always be positive. So covariance and R always have the same sign. Covariance can be negative, covariance can be positive. I just showed you that, right? But when I standardize, R falls between -1 and 1. And the best, the strongest is +1 R.
Is that close to 0.9, like the correlation?
The correlation here?
Yes. Because I
Well,
know
it's
that
going to be
from-
1. This one, if it's perfect, the R will be 1.
Oh, okay.
Like this one here, we could say, we're just guessing, you know, if I had actual numbers and the scale and everything here, but let's just say this would be closer to, like you said, 0.9 or something. It's positive 0. Let's say 0.85 or something like that. I don't know. It looks like a 9. Let's put 9.9. just to show you just some examples without numbers, just visually. Okay, what would this one be over here? What would the R be here?
1.
Oh, yeah.
What kind of
Got it.
one?
-1.
-1.
Excellent. So this would be R -1. And with all of that in mind, what kind of would you make this one? Relatively speaking, if this one's 0.9 positive, this one's going to be negative because it's kind of going down. Oops. It's going down. It's negative, but it's not very strong. I called it weak. So to be weak, it's closer to, it should be closer to what? What's in the middle of -1 and 1?
0.1.
So in the middle is 0. I'll show you an example of 0, but we'll make this negatives 0.3 or something. Okay. So
If
what
it's
would it,
close to 0, it's not like it
there's
becomes
no
less and less
relationship.
linear. Oh yeah, no.
Yeah, exactly. So we're just doing the patterns. If people like, want more details about this, I say watch the video. So this one here, what would this one be? What would the R be here?
0.
Yeah, good. So that's basically my review of regression that you need. Or you can say close to 0.
What's the range for strong and weak? Because like I heard it depends on the professor. Because I don't know.
There is sort of a rule, but I'm not going to get that specific here because I don't want to confuse you. But there's kind of a rule, and it has to do with how many observations there are. So yeah, go by professor. I think that's the right answer.
Okay.
Yeah, I mean, you guys can debate with me, so strong or weak. So why is this important, strong and weak? It's very important because if I have to make an estimate and I had to pick between all of these relationships, which one would I be more like, which one would I put my money on? Which one would I gamble on? Which estimate would be likely worth betting on?
First one.
Sorry, let's say where R is +1 or R is -1. Those are perfect relationships. I don't have data in some places. The rule is you should not make estimates. So let me show you what I mean estimates. So there's no data in here, right? There's no data in here. But if I wanted to estimate something in there, I use the line. Oops, very bad. I need my ruler. Let me get my ruler. Okay, so if I wanted to make an estimate in here for like 12.5 or something, you see there's no data there, but I could comfortably imagine there being a line here and using the line, which I didn't even write up. I'm going to write up the line in a second. And estimating, it should be like there. For a value from here, this should be my estimate here. That falls on the line. Sorry. Trying to do this as an estimate. So that's like 5, 10, 15, 20, a little bit under 25. If the value of X was here, I could estimate here. That's what it's used for. And I would be very confident about that. I wouldn't be so confident over here. This would be bad. This would be the worst. Shouldn't even try. I'd be wasting my money on that one, trying to see where that, if X was something, Y was something else. Look here. In this one, X here can be this value, this value. There's actually 2 different values for Y to be. So that's not a great place to make a bet, right? So my point is your estimate is as good as your correlation coefficient is good and strong. Okay. So let's go back to this. You guys can think about that. You can take a screenshot, or again, if you feel like you still need more background, please watch. You can watch it on fast, on fast speed to get my statistics review done before we get back next week together. Am I over time? We're done, right?
Yes.
Okay, so I'm going to tell you to do this before I leave. Do you guys have another class? Let me just tell you what I want you to do. I want you to read this document.
Tranquila.
So this, we have the covariance, correlation, and I calculate it different ways, but basically this is the easiest way to remember it, okay? I've just done it different ways, but that's not important. The important thing is that you should be able to do it every way, but that correlation is the standardized covariance. And finally, the last function or statistic you need is called the slope. And we calculated together and we made the line y equals
Me
a
puso en 3. Le puse vamos para.
plus bx. So who's on talking? Turn your microphone down, please. So what we did was make this equation of the line. And because it's statistics and not mathematics, we write it with a hat on it because we're estimating values and it's not
Sí.
necessarily exactly that value. This one is the slope. And this one is called the y-intercept. And we got them all out of our calculator. How good that line fits the data is given by the R. R of 1 or -1 means a perfect relationship. So I'm going to ask you guys to look. I know you're going to have your holiday, but and we're going to meet on Tuesday. Where I'm going to pick up is I'm going to talk about a different kind of data set with similar calculations, but because the data represents a population of data,
Me está llamando, amor.
my results are parameters. So that's what we're going to pick up. If you have time, review the statistics, and this is where we're going to pick up next class, and I'm going to get into Unit 5 material, okay? So have a good holiday.
Have a good holiday,
Thank
everybody.
you, as well. See you guys.
Bye.